Okay, we are at the desk and we would like to do lab 3.1 in terms of implementation. The equipments I need are not much different from the previous labs. I need a fixed box resistance. I already know 4.7, 6.8, 10, 10, 15, 22. Because some of the values that I have here, for example, if you take a look at this one, you can see this is 2.7, and I don't think I have it, and I have 10K, I do have it, 4.7, I have it. So I'm going to go ahead and utilize as much equipment as is available to me. Each desk is equipped with two variable resistance. This is, you have used this before. These two are going to give me the resistivity that is materialized through these nodes. So for example, if I want to have 2.7K, 2.7K means 2,700. So this is going to be, you can see that, that's going to be 2,000. This is 0, I'm sure of that. Then it's going to be 700, 2,700, 0, 0. So this is going to give me, this one is going to give me 2.7. So let's utilize that, and this one is going to be my load. I'm going to use that in a moment. If you take a look at my design, the design is still easy to manage. What you can do is the voltage source, the R1 and R2, you collect this, you make this loop, and then you bring in your R3, and then you are going to have the load. The load is going to be another variable box. That's why you need two variable boxes. So let's begin and building these each one at a time. So I'm going to go in, I'm going to go from the plus of the power supply into R1, and R1 is 2.7. It doesn't matter which side, I'm going to go into R1. So that's going to be my first step. I want to make sure everybody can see that. This is my wire. Okay. Now, after that, I go from R1 to R2. R2 is 10K. So from this end of 2.7, I go into 10K. So far so good. This one is my 10K, and after the 10K, I'm supposed to go back to my power supply. So this is going to be my loop. 4.7, 6.8, 10, 10, 15, 20. You need to remember that, please. Okay. I'm now gone to 2.7K. From 2.7K, I'm gone into 10K, and I've closed my loop. Now, the intersection of R1 and R2, the intersection of 2.7 and 10K, this is my intersection. This intersection is going to go into my R3. R3 is 4.7. This intersection is going to go into my R3. I close this loop. I have R3. R3 is 4.7. R2 is 10. R1 is 2.7. So from then, from the other side of 4.7, I'm supposed to go into my load. This is my load. For now, I'm just going to put it at some value. And then I'm going to go from, again, I'm not worried about the polarity here. The resistors don't have polarity unless the power is actually supplied. So that's going to be one side of my resistance. That's my load. And obviously, the load is supposed to come back to the power supply. This is the load from R3, which happens to be 4.7. I'm going to go into the load, and I come back to the same place as the power supply. So I'm coming back. Actually, let me pick up this big one. I'm coming back to the power supply. Simple. I close my loop. I brought in R3. From R3, I went into the R load, and I came back. Now, if you take a look at this table says turn on the system. I'm going to turn on the system. I'm going to make sure it's almost 20. So it's almost there. This is 20 volts, right? And then I'm going to change this so that the voltage across the load is going to be 2 volts, 4 volts, 6 volts, 8 volts, 10 volts, 12 volts. So I need a voltmeter. I need to turn this on. I'm going to grab this. You can see my voltmeter. On the paper, the voltmeter is going to be black on this node and red on this node. So I'm going to locate this pin that goes to the power supply and this pin also that goes to my voltage, and I'm going to make sure it's voltage. Usually when you turn on the system, it is by default set to voltage, to voltmeter. Now I want this to be 2 volts. I'm going to go into my variable resistance. I'm going to change that. So I'm going to go back. I want 2 volts. That's 4 volts too much. That's almost 2 volts. You can actually make it better by playing with these nodes. So that's relatively a good one. You can even go like this and then play with this one. You have the choice to play and grab the voltage and come back and make sure everything is fine. I need to make sure this is properly hold on to. So this is properly hold on to, and I'm going to play with this to make sure I get the value I want. Almost 2. That's the 2. I'm going to start reading it. I have 720. So the first one is 720. I made sure 720 ohm. Now for that RL, I've got 2 volts. I need to read my current. If you remember what we did for the current, we basically made sure that the current or ammeter is actually in series. So I'm going to turn this on. By default is a voltmeter. I'm going to make sure this is in the proper position. I'm going to push this for an ammeter. And the current that I am interested in is the current that goes through the load. So I'm going to take this off. You need to have your friends to help you, and you go back. Your current is 2.018 milliamp. That's this current. Okay? Now I want this to be 4 volts. Let's see. 4 volts. Almost there. 4 volts across this. Current is 1.7. It's dropping. I want this to be 6 volts. It's a good 6 volts. The current is further dropping. And eventually, if you want to simulate an open line, if this is open, this is almost milliamp. You see what I'm saying? Milliamp is almost 0 in this case. 0.158 milliamp is going to be extremely small. And in that sense, we are going to assume that this is almost open. It's not open though. It's about 90K. 90K from engineering point of view, it could be considered as open. So what is the idea? The idea is to change this resistor, make sure this is matching with the first row on the voltage, and this is the one you are going to read on the second row. Now, let me go back, turn off the system. What's the purpose of the second part? Okay. The second part says, after you calculate your R Thevenin and V Thevenin, you are supposed to build that Thevenin design. Suppose that R Thevenin happens to be 4.7. I'm just going to make a case. I haven't calculated it myself, but I'm going to go ahead and say that this is going to be, for example, 5K. And this is going to be 15 volts, right? So I'm going to go in from the source to my R Thevenin. From the R Thevenin to my load. You said this is about 5K, and again, I didn't calculate that. but if that's the correct value, 5K is going to be 5,000, 0, 0, 0, as well as this one 0. So this is my 5K, if it is my R Thevenin. And if this is my V Thevenin, I'm going to see to it in a moment. And then it is actually coming back from the other end of the load, to the black or the negative pin of the power supply. You said that you found V Thevenin to be, for example, 15. I'm just making a guess. So you need to make sure that this voltage is coming down to 15, or V Thevenin, whatever your V Thevenin is. You need to set this to R Thevenin, whatever your R Thevenin is. This is the same load. The same procedure is going to apply. I'm going to monitor the voltage across the load, right? I'm going to monitor that. Let's go back again, and okay, I'm going to start reading my current. The current is going to be read from this side, for example, or the other side, doesn't matter. And I'm going to change that. I'm going to see that this is this voltage I want. Again, you need to have a good colleague who can help you to make sure everything is set, or you can actually fasten them. That's another option you can do. So you need to make sure the voltages are there. For example, you want the voltage to be 4 volts, 4.3, and you read this. Then the voltage you want to be 6 volts, and you read this. Then you want to be 8 volts, and you read this. The entire idea is you want to see that the Thevenin equivalent design behaves the same way as this. So basically, I'm going to expect that these two would be almost the same, almost close. Unless something is wrong, I'm supposed to see that exactly the same. When we get to the power transfer, what is the idea? Actually, you do have that circuit already set for Lab 3.1. You already have it in this sense. So suppose that this is your R Thevenin, and this is your power supply, which is actually mimicking the Thevenin voltage, V Thevenin you found, and this is your RL. We are going to do the same thing. This time, R Thevenin is given to us. We already know through the calculation. Times 0.2, that's my RL. I know what my RL are going to be. This is my RL. I'm going to change the RL, and each time I'm going to record VL, IL, and I'm going to move on. And I'm going to calculate PL, and PS is also given to us, and I want you to be able to verify the graph we talked about in terms of voltages and currents. The entire idea is the graph is supposed to reach its maximum value, just the PL, its maximum value when this RL is the same as this. If it is less than the R Thevenin, it's not PL max. If it is more than R Thevenin, it's not P max. Of course, VL could be coming from 0 to infinity. 0 to V Thevenin. IL could be coming in from I Norton or I short to 0. I know that part. But in terms of VL, what is happening, I'm going to actually verify that through the experiment Lab 3.2.